Welcome to iLecture Online, and in this example we're going to look at projectile motion in the general format or the general approach. We're simply going to shoot out a projectile at some initial velocity at some angle theta above the horizontal, and we're trying to find the range of this projectile, meaning how far will it go before it hits the ground, and that's known as the range of the projectile. So we simply follow the same standard procedures before. The first thing we want to do is find the components of the initial velocity. Find the x and the y components of v initial. And we do that the same way as before. So we assume this to be the x component, so v initial in the x direction. This is the y component, v initial in the y direction. Of course, that's going to be the hypotenuse, v initial, times the cosine of the angle theta. And here it is going to be v initial times the sine of the angle theta. So there's your x and y components of your initial velocity. The second step will be to find the time in the air. So time in the air is equal to question mark. All right. So again, we use the same equation as before. Only the vertical motion determines the time in the air. So we have y equals y initial, down, plus v initial in the y direction times time plus 1/2 gt squared. All right, now what do we have? Well, our final height and our initial height will have to be 0 because it starts on the ground and it ends on the ground. So we have 0 equals 0 plus, what's our v initial in the y direction? Well, we have it right here, which is v initial times the sine of theta times t plus 1/2 gt squared. And now we have to solve this equation for time. Well, let's see here. We can factor out a t. So we have 0 is equal to t times v initial times the sine of theta plus 1/2 gt. All right, now we have a product of t times what's inside the parentheses. And so whenever we have a product of two things and the product equals 0, that means one or the other has to equal 0. That means t is equal to 0 or v initial sine of theta plus 1/2 gt is equal to 0. Of course, that's equal to 0. We move that across right here. So we have 1/2 gt is equal to minus v initial times the sine of theta. And of course, I multiply both sides by 2, divide both sides by g. I get t is equal to minus 2 v initial sine of theta divided by g. Now you say, well, wait a minute, I have a problem here. Why do we have a negative here? We can't have negative time. But remember that g is a minus 9.8 meters per second square, which will negate that negative. Sometimes, in this case, it's simply easier to think of g as simply 9.8 and then remove the negative so we don't have any confusion. So typically speaking, we would write that the time is equal to 2 v sub naught sine of theta divided by g, simply assuming that I'm going to be dealing with a positive g. So we just put right here positive g, and that's a more simple form of the equation. All right, now that we have time in the air, now we can figure out how far this object is going to go. So for that we use the equation x is equal to v initial in the x direction times time. So we have the v initial in the x direction right here. So we have x, which is the range, is equal to v initial times the cosine of theta, and we multiply that times what we got for time, which is 2 v sub naught sine theta over g. So that would be 2 v sub naught sine theta over g. And if I simplify that, I get x is equal to 2 v sub naught squared over g times the cosine of theta times the sine of theta. Now, we can actually simplify that because it turns out that there's an identity, a trigonometric identity, that says that 2 times the sine of theta times the cosine of theta is actually equal to the sine of 2 theta. All right, if we use that identity and we replace that in here, we can say that x, or the range, r, is equal to v sub naught squared times the sine of 2 theta all divided by g. And that's the equation we can use to find the range of a projectile that is shot off from the ground at any angle theta and at any initial velocity v sub naught. Now let's take a quick look at that equation. So the range only depends, of course, on the initial velocity and on the angle theta. And what if I want to find the maximum distance, the maximum range of a projectile? Well, let's see here, the sine of 2 theta. We know that theta can vary from 0 to 90 degrees. So we know that 0 is less than or equal to theta, which is less than or equal to 90 degrees. If we plug in 0, the sine of 0 is 0. So if the angle theta is equal to 0 degrees, we know that the range therefore must be 0, because the sine of 0 is 0. If we plug in 90 degrees, theta is equal to 90 degrees, then of course 2 times 90 degrees is 180 degrees, and the sine of 180 degrees is 0 again. That means that the range is also 0. And that makes a lot of sense, because if we make the angle 0 degrees, then of course there's no height and the projectile won't get anywhere. If the angle is 90 degrees, then the projectile will go straight up and down, and of course again the range will be 0. So the range can only be non-zero for angles between 0 and 90 degrees. So at what point will we get the maximum range? Well, we'll get that when this component here is as large as possible. And so when is the sine of an angle as large as possible? Well, when the angle is 90 degrees. And so twice the angle should equal to 90 degrees. So 2 times theta should equal 90 degrees, which means that theta should be 45 degrees. This means R will be a maximum. And so then R max can then be assumed to be V sub naught squared over G times the sine of 90 degrees, which is 1. And so this is the equation for the maximum possible range for a projectile. And that is how we do a problem like this. So now we have a nice equation for our use to find the range or the maximum range of a projectile. Again, the methodology is the same. Find your components first, then find time in the air using this equation, then plug it into this equation, because you know that in the horizontal direction, velocity is constant. We plug in the initial velocity of the x direction, the equivalent on time, and we get this nice equation. Remember again that in this case, g is a positive 9.8. We did that to get rid of this negative sign over here. All right, and there's a nice introduction to how to find the range of a projectile, and in the next video, we'll show you an example of how to utilize that equation.